Let's look at this application problem in the logarithmic and exponential functions derivative section. In this one, we have a quantity of iodine that's, I guess, in the body T hours after it's given. And the quantity is the equation, in this case, 750 times the exponential function, base 1/2, raised to the time that it's in the bloodstream divided by 13.1 power. Okay, so I went ahead, wrote down my exponential function over here that represents the quantity. Now, the first question that's asked here is it's wanting us to determine the time it takes for the iodine to drop to 10. So, well, that's the quantity in the bloodstream. So I set that quantity equal to 10 and I solve for t. So I need to find the time at which that happens. So this is just solving an exponential equations. This would be like a pre-cal problem. In order to get the t solved for, we need to get the exponential function by itself first. So you'll see that's why I divided by 750 on each side. That got the exponential function base 1/2 all by itself on the right. And then I needed to get rid of the exponential function. At this point, I could have taken the log base 1/2 of both sides. I opted to do a slightly different technique and just say, well, let's just take the natural log of both sides. I took the natural log of the left-hand side and then the natural log of the right. When I took the natural log of the right, I went ahead and used the principles of logarithms that said, well, if you're going to take the natural log of the right-hand side, then its exponent can and should come down in front of it. So the natural log of the right-hand side is the exact same thing as the natural log of 1/2 times t over 13.1. Now, this was the key point in solving this exponential equation for t. So now if I want to isolate t all by itself, I say, well, it's just the natural log on the other side times 13.1, since t was being divided by 13.1. And then I'll need to divide by the natural log of 1/2, since previously t was multiplied by that. So this is my correct exact expression for t. And then when I typed that into the calculator to get a decimal answer, I got 81.5975. Of course, it kept on going on. This is an irrational number. The page is wanting us to round to the second place. So that would just be 81.6 hours. So after 81.6 hours, the amount still present in the body would be a measurement of 10. So now, the part B, C, and D are all extremely similar. They ask us how much the rate of change the iodine is in the bloodstream, or the iodine is in the bloodstream. In B, it's 18 hours. In C, it's 24 hours. And then D, 3 days, 72 hours. So all I need to do is take the derivative and then evaluate it at all these different places. So the directions for B might as well say find Q prime evaluated at 18. I have to take the derivative of that function, so I went ahead and rewrote my function right here. And then the derivative of any exponential function is that exponential function, so I just rewrote the exponential function, times the derivative of its exponent. Instead of writing that exponent as t over 13.1, which is fine, it's easier to see the derivative of that exponent if I write that as the equivalent expression, and that exponent is 1 over 13.1 times t. Now when I say times the derivative of the exponent, it's easy to see, well, the derivative of the exponent is just its coefficient. And then times the natural log of the base. Well, the natural log of the base is natural log of 1/2. This is my correct derivative expression. Now I just need to evaluate that derivative expression for part B at 18, for part C at 24, and part D at 72. And then the last question is asking us to understand what's going on. And it says, what do your answers say about the rate at which iodine decreases as time increases? Well, notice after 18 hours, its rate of decrease was negative 15.31 the units in this case, units per hour. After 24 hours, the rate of decrease had slowed down to only negative 11.15. After 3 days or 72 hours, it had slowed down to only negative 0.88. Well, what that's showing you is that there's almost none left in the bloodstream at that point. So as it decreases in the bloodstream, the rate of decrease will continually decrease as well, because it can't keep on decreasing at the same rate. And so we can say, well, as time goes on, the rate of decrease is going to decrease eventually to 0 in case you have some more iodine put into the bloodstream. So for part C, the rate at which iodine decreases is decreasing as time increases. And that's just represented by these answers continually getting closer and closer to 0. Thus, its rate of decrease was decreasing. All right, guys, hopefully that makes sense with this one. It's a pretty good problem.